Hey everyone, and welcome to this explainer. Today, we're going to decode the absolutely fascinating, rule-breaking chemistry of group 15 elements. Our big theme here is actually pretty simple, but it is incredibly powerful. If you understand the molecular structure, you never have to blindly memorize a reaction again. We're going to prove that structure literally dictates destiny. Let's get right into it.
Right off the bat, let's dive into a crazy chemical mystery. How can two elements, nitrogen and phosphorus, sitting right next to each other in the exact same family, behave so completely differently? I mean, think about it. Every single breath you take is mostly nitrogen, right? Totally harmless, completely inert. But then you have its sibling, white phosphorus, which is so aggressively reactive it will literally spontaneously combust if it even touches the air. Talk about extreme sibling rivalry.
So, here's our game plan to figure this out. First, we'll look at the group 15 family. 2. Nitrogen's chemical vault. 3. The nitrogen oxide spectrum. 4. Nitrogen's powerful oxoacids. 5. Phosphorus, the shape-shifting sibling. And finally, 6. Decoding phosphorus acids.
Okay, part 1. The group 15 family, the baseline and the rebel. So every element in this group, starting from nitrogen all the way down to bismuth, shares a defining ns2-np3 outer shell electronic configuration. Basically, they all have 5 valence electrons. But what's really cool is how their physical states shift. The family transitions beautifully from true nonmetals like nitrogen and phosphorus at the top, down into metalloids like arsenic and antimony, and finally ends with a true metal, bismuth, right at the bottom.
Now, here's the kicker. Despite sharing that exact same electron blueprint, nitrogen acts like the absolute rebel of the family. It just breaks all the rules. Why? Well, it comes down to its incredibly small size and really high electronegativity. But the biggest factor? It has 0 d orbitals. None. This forces nitrogen atoms to bond with each other using extremely tight, unbreakable triple bonds. That incredibly high dissociation energy is exactly why the nitrogen gas floating around us right now is completely unreactive. I mean, it takes massive energy, literally a lightning strike, just to break it apart.
Moving right along to part 2, nitrogen's chemical vault, a spectrum of states. Because of that highly unique, tightly packed electron setup we just talked about, nitrogen can exhibit a massive, incredibly diverse variety of oxidation states. It swings wildly, all the way from a -3 when it bonds with hydrogen in ammonia, up through 0 in pure nitrogen gas, and all the way up to a +5 in powerful compounds like nitrogen pentoxide and nitric acid. This wild flexibility, that's the engine driving its complex chemistry.
Which brings us to part 3, the nitrogen oxide spectrum, redox mechanics.
To really wrap our heads around these reactions, we need to talk about a totally fascinating concept, the disproportionation reaction. You can basically think of this as chemical multitasking. It's a specific type of redox reaction where an element in a single substance is literally fighting with itself. It is simultaneously oxidized, meaning it loses electrons, and reduced, meaning it gains electrons at the exact same time. Crazy, right?
Let's look at exactly how this works. When nitrogen dioxide, that toxic acidic brown gas you sometimes see in severe smog, when that reacts with water, the +4 nitrogen completely splits its identity. Part of it oxidizes up to a +5 state, forming nitric acid, HNO3. But the other part is simultaneously reduced down to a +3 state, forming nitrous acid, HNO2. It is a perfectly balanced chemical dance.
All right, part 4, nitrogen's powerful oxoacids, chemical forensics.
Now those oxoacids we literally just formed, nitric and nitrous acid, they have entirely different chemical personalities. Nitric acid is an absolute powerhouse. We're talking about a strong, highly stable oxidizing agent famous for dissolving notoriously unreactive metals like copper and silver. On the flip side, nitrous acid is super weak and incredibly unstable. It's so indecisive, acting as both an oxidizing and a reducing agent depending on what it mixes with, and it'll even spontaneously undergo disproportionation right there in the water.
Since nitric acid and its nitrate ions are so critical in chemistry, we need a bulletproof way to detect them. If we're playing chemical detective in the lab and want to find those powerful nitrate ions, we use a classic forensic procedure called the brown ring test. You just take your sample, add some freshly prepared ferrous sulfate, and then, very, very carefully, let concentrated sulfuric acid slide right down the wall of the test tube. If nitrates are hiding in there, a distinct brown ring magically forms right at the junction where the two liquids meet.
But here's the coolest part. The actual chemical culprit making that brown ring isn't just dirt or rust. It's the creation of a really fascinating complex ion, FeNO2+. What happens is the nitrate ion reduces down to nitric oxide gas, which then chemically traps itself onto the iron, forming this highly specific, highly visible brown complex.
Okay, let's switch gears. Part 5. Phosphorus, the shape-shifting sibling.
Let's look at the absolute stark difference between two allotropes of phosphorus. Think back to white phosphorus. Its P4 molecule is locked in this incredibly tight, highly strained tetrahedron. Those 60-degree bond angles are practically screaming to break open. This makes it so reactive it'll spontaneously combust in the air. Basically, it really wants to burn down your lab. That's why we have to store it safely underwater. But then you have red phosphorus. It relieves all that terrible structural strain by popping open those bonds and linking together to form long, stable polymeric chains. It's the exact same element, but a totally different destiny, based completely on structure.
Now, when that super volatile white phosphorus does burn in oxygen, it creates phosphorus pentoxide, or P4O10. This complex, caged-like molecule is so fundamentally desperate to absorb water that it acts as one of the most phenomenal dehydrating agents in all of chemistry. It literally rips water molecules straight out of other compounds, morphing itself into phosphoric acid in the process.
And that leads us to Part 6, Decoding Phosphorus Acids, the Basicity Trap.
Okay, consider the formula for hypophosphorous acid, H3PO2. If you're looking purely at those letters and numbers, you might logically assume, oh, it has 3 hydrogens, it can donate 3 protons, right? I mean, it literally says H3 right there at the front.
Well, actually, drawing out the Lewis structure reveals the trap. You've got a central phosphorus atom double bonded to an oxygen, single bonded to another oxygen, and then single bonded directly to 2 hydrogen atoms. Because only the single hydrogen attached directly to that highly electronegative oxygen atom can actually be released into solution, this acid isn't triprotic at all, not even close. It's completely monoprotic. It only gives up 1 single proton.
So here is your crucial takeaway, your golden rule for today. Structure dictates basicity. You absolutely cannot just look at the chemical formula. You have to look at the Lewis structure. Specifically, you need to count the POH bonds to predict how many protons a phosphorus oxoacid will donate. Those pH bonds, they're literally just along for the ride. They do not participate in the acid's basicity whatsoever.
And hey, just like our forensic brown ring test for nitrogen earlier, we have a slick way to identify these resulting phosphate ions in the lab too. You just take an aqueous solution, add a little silver nitrate, and boom, a chemical reaction kicks off yielding silver phosphate, Ag3PO4. And that shows up as this very distinct, bright yellow precipitate. It's just beautiful, definitive visual proof of the exact structure we've been tracking. So, we have covered a ton of ground today, but it all loops back to our main theme. By understanding the real, physical limitations of nitrogen's tiny size and its lack of d orbitals, and by mapping out the severe bonding strain of white phosphorus, we've successfully mapped their incredibly complex behaviors. We didn't just blindly memorize a bunch of equations, we let the structure tell us the whole story. But keep in mind, we've only decoded the top 2 siblings of group 15 today, which leaves us with a pretty thrilling question. If nitrogen is so stubbornly inert and phosphorus is so wild and explosive, what bizarre, unpredictable structures and reactions are waiting for us as we travel further down the periodic table to heavyweights like arsenic, antimony, and bismuth? Keep that curiosity alive, keep studying those structures, and we'll explore exactly that in the next explainer. See you then!